We're going to look at how vectors allow us to make deductions and solve problems involving geometric shapes. Even if we're dealing with three-dimensional points in space, we can still use the fundamental definitions of these various shapes to solve problems. I'd recommend you pause for a minute and see if you can write down the defining features of each of these common mathematical shapes. It's quite possible that there'll be a few in this list that you're a bit rusty on, and maybe you haven't talked about them or used them since GCSE. So there might be a couple of things you have to look up or refresh your memory on. Once you've done that, come back. We'll talk about exactly how you might interpret a set of points to determine whether or not they form a shape like this. So let's start with the isosceles triangle. The defining feature of an isosceles triangle is that it has two equal sides. If you want to be really specific, it has exactly two equal sides. If all three sides are equal, then it will be an equilateral triangle instead. Depending on the broadness of your definition, you could argue that an equilateral triangle is also an isosceles triangle. But if you're asked to prove a triangle is isosceles, it'll be because it's isosceles and not equilateral, in the same way that if you're asked to prove that something is a rectangle, chances are it won't also be a square. So for an isosceles triangle, it will be helpful to be able to calculate the length of a line between 2 points. Well, in 3D space, we can construct a vector between one point and another, provided we know the coordinates of the points, and then we can use Pythagoras, even in 3 dimensions, to calculate the length of that line. You can do a similar thing with the equilateral triangle. If you find the vector between each of the corners and the next, then you can work out the length of each vector using Pythagoras, and you'll quickly be able to identify whether or not 2 of the sides are the same or all 3 of the sides are the same. For a trapezium, this is the most basic in some ways of the quadrilaterals, the 4-sided shapes. In order to be a trapezium, the only condition you need to meet is that at least one of your pairs of sides are parallel. If you can demonstrate that the vector from, say, A to B is parallel to the vector from C to D, then you've got a trapezium on your hands. It's possible that you have more than just a trapezium. If those two vectors are not just parallel but also the same length, then you're looking at a parallelogram. And of course, depending on the length of those lines and the length of the other lines, you might be dealing with a rhombus. A parallelogram, remember, has 2 pairs of equal length parallel sides. So it's equivalent to a rectangle where you may be allowed to mess with the angles, but you can't mess with the side lengths. A rhombus is like a parallelogram, but it has the added restriction that all the sides have to be the same length. So you could still prove that a shape was a rhombus by demonstrating that opposite sides were equal in length and parallel, and that all 4 sides were equal in length. If you could demonstrate in addition to that that the angle between one side and another was a right angle, then you'd be dealing with a square. Similarly, if you've got a parallelogram that has a right angle at any of its corners, then it must have a right angle in all of its corners, and it must be a rectangle. A kite, the requirement for a kite is that the length of 2 pairs of adjacent sides are equal. So if you've got a shape ABCD, we need AB and BC to be the same length, and CD and DA to be the same length, for instance. In some ways that's similar to a rectangle, but the order in which the side lengths come is different. So instead of the opposites being the same, it's 2 adjacent sides being the same. Okay, here's a few things we can do with vectors that you'll find helpful if you're trying to prove any of these things, or if you're trying to find a point that satisfies the condition these must form a rhombus or a kite. To start with, if you've got the coordinates of a point, you effectively already have the position vector of that point. We'd write the coordinates horizontally, x1, y1, z1, but we'd write the position vector vertically, x1, y1, z1. And we'd call that position vector OA with an arrow over the top to represent the fact that it's an instruction for moving you from the origin to the point A. Now, if we want to go from A to B, then we need the coordinates of B relative to A. That's why we do x2 minus x1, the coordinates of B compared to A. And it makes a lot more sense if you try putting some numbers in. If A has x coordinate 2 and B has x coordinate 5, Well, the vector AB needs to move you 3 in the direction of the x-coordinate. So 2 add 3 will give you 5. Therefore, the vector AB needs to be calculated by subtracting the vector A from the vector B. We can test if two vectors are equal in length. We would use Pythagoras. So if the length of a vector happens to be the same as the length of another vector, even if they're pointing in completely different directions, when you apply Pythagoras, a squared add b squared add c squared square rooted, then you'll get the exact value of the length and you can compare it to any other vector. You can test if two vectors are parallel by checking to see if one vector is a scalar multiple of another one. And generally speaking, for these sorts of questions, we don't mind if the two parallel vectors are in the opposite sense. If, for instance, you have a shape ABCD and you're trying to prove it's a rectangle, you might demonstrate that AB and CD are the same length and they're parallel, but maybe CD is equal to negative AB. Well, that's fine. It just means that you're moving to the left along the bottom line of the rectangle. It doesn't have to be an identical vector. It just needs to be either the same vector or the negative of it to be the same length and parallel. And the last thing is, what if they're equal in length and parallel? If they're also going in the same direction, then it's just a case of testing if the two vectors are equal. So if they're completely equal vectors, then you can just make them the same. This is really useful if you're constructing for yourself a shape. If you need to make a square, for instance, and you've already got 3 of the corners, well, you can use the vector that represents the bottom edge in order to construct the top edge. So if you've got a vector that takes you from bottom left to bottom right, then you can use that same vector to take you from the top left to wherever the top right corner ought to be. You'll see how it works when we go through some examples. So here's our first example. We've got 4 points. I've written them out as position vectors rather than the coordinates because that's what we'll be using them for. And our job is to determine the type of shape ABCD. The first thing we look for is the vectors that represent the edges of this shape. So if you were to go from A to B, what instruction would you be following? The vector AB is equal to OB minus OA. So we've got the vector OB, 11, 2, minus 9, and the vector OA, 7, 12, minus 1. If you subtract one from the other, that gives you an instruction which, if you follow it, should get you from the point A to the point B. And you can check that that's what happens. Do a little bit of a gut check and make sure it makes sense in your head. If you go from 7 to 11, you are adding 4. And similarly for the other terms. From 12 to 2, you're taking away 10. From negative 1 to negative 9, you're taking away 8. We can do the same thing with BC, the vector from B to C, and then CD from C to D, and finally DA from D to A. And it doesn't really matter much if you do DA or AD, you're still finding a vector which somehow represents that edge of the shape. And what we're most interested in is which way they're pointing and the length of those vectors. Well, we're going to start by looking at the most obvious one. It's easiest to look for parallel vectors first. So we're going to investigate each pair of these and see if we can identify any parallel vectors. That may seem like quite a tedious job. I mean, you've got 4 different vectors and you're trying to identify any pairs of them. There are actually 6 different pairs amongst these 4. We could have the first and second, first and third, first and fourth, second and third, second and fourth, third and fourth. However, we can make life a bit quicker for ourselves by treating the vectors a little bit like equivalent fractions. If you're trying to find out if 2 fractions are equal to each other, the easiest way to deal with it is to simplify both fractions to their simplest form and then compare directly. If the simplest form of your fraction is different to the simplest form of mine, then there's no way the 2 fractions are going to be equal. That's what I'm going to do with these. So AB can be simplified. We can divide through by 2 and we get 2, negative 5, negative 4. Now we could simplify one other. We can simplify CD. If we pull out a factor of 3, then we get negative 2, 5, 4, which sounds familiar. In fact, if we go one step further and pull out a factor of negative 3, we'll see that both vectors AB and CD are multiples of some other simpler vector, 2, negative 5, negative 4. Well, if they're both parallel with that vector, then they're both parallel with each other. and in fact we can rearrange a little bit and we'll see that the vector AB is negative 2/3 multiplied by the vector CD. So AB and CD are parallel. It's fairly easy to see that none of the others are. They're already in their simplest form, if you like. In other words, BC and DA, none of their elements have any common factors, so we can't write them in any more fundamental way. And that makes it obvious that none of them are multiples of any of the others. But if we've got just one pair of parallel vectors, and crucially we've also noticed that they're not the same length, and there are no other parallel vectors involved. In fact, the only way for the other two to be parallel would be for these two to be the same length, then we'd be dealing with a parallelogram. But since we have just a pair of parallel lines, and that's it, we know we're dealing with a trapezium. Remember the rule for a trapezium, one pair of parallel sides, that's all. If there is something stronger, some additional condition, then we would investigate that. We'd look into maybe all the sides are the same. We might be dealing with a rhombus or a square. Maybe we have two pairs of parallel sides, in which case we're looking at a parallelogram. But in this case, there was nothing further than a single pair of parallel vectors. Therefore, we're looking at a trapezium. This next question has a little bit more to it. To start with, we're asked to prove that shape ABC is an isosceles triangle. Then we need to find its area, which is not as simple as it sounds, and then find the point D such that ABCD is a parallelogram. We'll get to the parallelogram bit in a moment. Let's start with showing that ABC is an isosceles triangle. And we're going to do it in a similar way to what we did before. We've got the coordinates of the corners, but I'd like to find the vectors between the corners. So AB is a vector that represents the journey from point A to point B. It follows along the edge from A to B. Similarly, BC and CA. Now hopefully you can see already why we might be dealing with an isosceles triangle. You might be forgiven for thinking that AB and BC were actually parallel. They're not, because the negative signs are in different places. They both have 3 as their middle term, but AB has a positive 2i and a negative 2k, whereas BC has a negative 2i and a positive 2k. So they're pointing in slightly different directions, but the size of each element corresponds. So I shouldn't be surprised when I do a bit of Pythagoras to discover that AB and BC both have length root 17. And remember, you should leave it as root 17, not 4 point something, because you're trying to demonstrate that these two are exactly the same. And you can never prove two things are exactly equal by showing that they are approximately the same. The last thing I would do for completeness is to calculate the length of CA. Hopefully you won't be surprised that CA has length 6, because it moves no distance in the x direction, 6 in the negative y direction, and no distance in the z direction. If it's only going in the y direction, then all we need to look at to figure out how long it is how far it goes in the y direction. So of course it has a length 6. That makes it the longest of the 3, because root 17 is just a bit bigger than 4. But because we have 2 sides that are equal, and the third side which is different, we know we're dealing with an isosceles triangle. For the next part, we're going to see if we can work out the area of this triangle. I've kept the information we had from the beginning about the vectors AB, BC, CA, but we're going to do a bit more work here. We're going to draw a sketch, and I should stress here we're dealing with 3-dimensional vectors. Drawing a 3-dimensional vector sketch is not something that's either necessary or particularly helpful for you. It's going to take a long time, it's going to be difficult to do, and it won't be any more enlightening than drawing something 2-dimensional. As long as you remember that what you're drawing is not an accurate representation, it can still be very helpful. So I'm going to use the fact that I know we're looking at a triangle which is isosceles and where the lengths AB and BC are equal. If I want the area of this triangle, well, there's a few different methods that spring to mind. Half AB sine C. It's a perfectly valid one to use. We'd need the length of 2 of the sides and the size of the angle between 2 of the sides. Even without having learnt some additional vectors methodology which allows you to find angles between vectors a bit more easily, which you're not going to get onto this year, so don't panic about it. It's still possible to find the angle between two sides here because you've got a triangle where you know the length of all three sides. You could use cosine rule to find the missing angle, and then half AB sine C to find the area. And that's a perfectly valid way to do it. I'm going down a slightly different route using the vectors themselves, and it's not necessarily quicker and more efficient, but hopefully it shows you an alternative method and helps you to make sense of what vectors can do. Since it's an isosceles triangle, I can see a relatively nice way to make use of the half base times height method. I need to figure out the height of the triangle, but my triangle is symmetrical, so I can use that to drop a perpendicular line straight down from B to the base AC. So that's what I'm going to think about. We'll use CA or AC as the base, and we're going to introduce a new point called M, the midpoint of that line. If we drop a line from B to M, then the length of that line is the height of my triangle, because that line is the line of symmetry for my isosceles triangle, so it must be at right angles to the base AC. In order to find M, I'm going to need to start from C and move halfway from C to A. Equivalently, I could start from A and move halfway from A to C. I've already got the vector CA, which is why I've done it that way around. OC is a vector that I have at the beginning, 275. CA is a vector I calculated, is how you get from C to A. And you can see that instead of being at 275, we're at 245. We've moved 3 in the negative y direction, because that's the direction that we're following if we're going from C to A. This gives me the vector position of M. In order to get MB, I need to find a vector for B relative to M. So OB minus OM will give me MB. We have OB already, and OM we've just calculated. And the bit we care about is the length of MB. And it might be worth checking that this is reasonable. I've got a diagram which is not far off being an accurate diagram. AB and BC are slightly shorter than AC. We're getting a value for MB which is 2 root 2. It's just less than 3, because 2 root 2 is root 8, which is just less than root 9. So if that length looks reasonable according to a diagram, then that's usually a good sign. The last bit to do is put it together. Half base times height. The base we already know is the length of CA, which we already have, 6. And the height is going to be the length of this new vector we've created, which takes me from M to B, which is 2 root 2. And we get a nice exact value for the area, 6 root 2. The final part of this question is asking us to find a point D such that ABCD is a parallelogram. And the first thing I want to notice is that it says find a point D. There are quite a few different possibilities here. Here's one option, and I've drawn this out a bit more precisely so the lengths are a bit more realistic, but the idea behind this will work just as easily even if your diagram looks a bit different. I've got the triangle ABC shaded in blue, and I've shown how by using the same vector as BC, starting from A, I can generate my fourth point. And because BC is parallel to AD in this diagram, we definitely have as a parallelogram. However, you don't have to go from B to C. You could go from C to B, and you could start from A and move in the opposite direction. In fact, there's quite a few different alternatives. You can pick any of the sides you like and go in any direction you like, and you will create for yourself a parallelogram that has the 3 points you've already got and a fourth. Now, there's not quite as many options as you might think from this picture. In reality, there are only 3. If you look closely, you'll see the way I've grouped them together will show you. The parallelogram you end up with is the same whether you go from A and you follow BC, or you go from C and you follow BA. They'll both end up in the same place. This is the same point as this one. Similar things happen over here with the other two. All we need to do to find a point D is to choose a point and add the vector that goes between the opposite 2 points. So if we pick the point A, we need to follow the vector BC or the vector CB. Either of them will be fine. If we choose the point B, we'll need to follow vector AC or vector CA. That way, we'll be starting from a corner that we know is on our parallelogram, and we'll be moving in the direction of the opposite side to generate a new side which is both equal and parallel. The length is the same and the direction is the same, so it's basically the same vector. We're going to follow that vector along, and that will get us to the new point. If we do that, we can find OD, in other words the position vector of this fourth point D. We get that by doing OA, which is the position of A, plus BC, which is the vector that takes me from B to C. This one's following the very first diagram I've got. So the vector BC would take me from B to C, but I can equally well follow that same vector starting from A, and it will take me from A to the mystery new point that I'm trying to get to, D. That gets me to the point 0, 4, 7. I want to remind you at this point, all you've drawn, if you have drawn anything, is a two-dimensional diagram, which does not tell the whole story. So there's not a lot you can do with that 0, 4, 7 to verify it particularly. It's going to be somewhere funny in 3D space, and if you imagine holding up a parallelogram in 3D space, moving it and turning it round, you could put it in all sorts of funny orientations, and it wouldn't be immediately obvious from the coordinates whether it was or wasn't a parallelogram. Just for completeness, you can see that the two on the left both have the coordinates 0, 4, 7. It doesn't matter how you go about finding that point, but the next two, using this method, starting from A and following vector CB, or starting from B and following vector CA, will get you to the point 4, negative 2, 3, which also forms a parallelogram for the same reasons, and it'll be a perfectly valid answer. The last option is 4, 10, 3. Both of the last ones would get you to a different point, the point 4, 10, 3. It's worth trying this all on the same diagram, and you'll see that you construct some sort of bigger triangle where the original corners A, B and C form the midpoints of the sides of that bigger triangle. But every single one of those shapes that you would have produced is a parallelogram, and any of those three different possible points that we've constructed would form a valid parallelogram.